Okay. Morning, everyone. Yeah. So we're going to start. I hope you had a good weekend. So last Thursday we started talking about milestone 3. I hope you guys started out in milestone 3. If not, I hope you at least started dividing the tasks. We have less than 2 weeks for the deadline. And we started talking about some of the algorithmic approaches to attack the pathfinding problem. And we're going to talk about this in this and the next lecture as well. Okay, so just a reminder, the first algorithm we introduced was depth-first search, and it is basically similar to an algorithm you've used in ECE294, where you're trying to find a node inside a binary search tree. So we have this the declaration of a function to find the path given the current ID and the destination ID. So initially the current ID is the source ID that we will start at. Okay, so first we check the base case, which is if the current ID is equal to the destination ID, then we return true. That means we found the path. If not, we recursively go over all of the children or neighbors in the graph in order to find the path from there. So we take what the current node is, okay, and then for each outgoing edge of this current node, we build the graph somehow with this struct node that is shown here, that basically stores all of the edges connected, all of the neighboring intersections connected to that node. You have methods from milestone 1 that allows you to do that. Okay, so for each of these edges, we now call the find path again, given that the current ID is now that intersection or that neighboring intersection. If we found that, then we return true. If we go over all of the children and we end up not finding anything, then we return false. That means we couldn't find a path, and that is a valid edge case in our maps. Some of them, for example, if you try to find an intersection to an island, to an intersection in the island, then we can find a path. Okay, so if we go over quickly go over this example, we go over the source. First, we visit this number 2. Then we go to number 3. We couldn't find a path, so we return up. And then we go back, visit this node again because it's a child of 2. And then, okay, we reach the destination. And that's our path. Now, we talked about this in the previous lecture as well. The problem with depth-first search in this case is that it is not generic enough to work on generic graphs. In binary search tree, it works because each node has 2 children and there are no cycles in the tree. But in a generic graph, like a city map, there might be some loops. So let's say that we started at this source, and then we want to get to this destination, and let's say we visited this first, okay? But we decided to visit this child of this node first, and then we kept going right. So at this node, we have 2 possibilities. Either go back to this node or go to the destination. But for some reason, we randomly chose to go back to the other edge. And because there is nothing that tells us that we have visited this node before, we will keep going into this infinite loop. Okay? So we fixed this by introducing a new, an additional flag to the node data structure called visited. This basically marks each node as either visited or not. If we visited, then we don't have to go over finding the path from its children again. Okay, so after the base case, we set the visited flag for the current ID to true, and when we visit each node, we don't go to the recursive function unless it hasn't been visited before. So we first check that the nodes of the whatever next node is not visited, and this allows us to break the cycle. And for example, look here, we are marking each node as visited, and then when we reach here, we check that, okay, this edge has been visited, so we're not going to check it. Let's go to the next one. And in this case, we found the path. So some of you asked last week that do we need to actually mark some of the nodes that have been visited unvisited again? And the answer is no. And this example shows us how. So let's say we start at this source, okay, and our destination is here. So we mark this first node as visited. Then we went to this node. We mark it as visited, and now there is only 1 child, right? Okay, so we will mark this as visited now we couldn't find a path, we return false from this case, right? So now we are here. Since we return false here and there are no other children, we go back to the source here, and now we have to visit other children. Okay, so we reach to this node and we mark it as visited. Now this node has two childs. It can either go here and it can go to the destination. Let's assume that we mark this unvisited again, okay, at some point. If we visit it again, we will end up going through this same path again, and we won't find a path. So, yeah. No, there was a question last week asking, should we mark it unvisited again, right? And we guarantee that if we mark a node visited, you don't have to visit it again, even if you get to that node from a different case, right? So I'm just saying, for the sake of explanation, let's say that we marked it unvisited, right? So we will have to go through this again, because now this is a node that is not visited, and we will have to go through this same path again. So we are kind of doing redundant work that is not needed, because we know for a fact that there is no path reaching the destination if we start at this node. So we don't have to mark a node unvisited again, okay? And if we don't do that, then the next child will be the destination in this case, and we found the path. Okay, so what do we know so far? Right now, the output is just a Boolean flag. That means if we found a path or not, okay? In M3, we tell you a good way to encode the path is a vector of street segments, and we actually tell you to return that vector, okay? But in this algorithm, all we know is whether, we only know very little. We only know if a path exists or not. So if we're going from College and Spadina to, let's say, Bloor and Young, it will return true. If we're going to an intersection on the island, it will return false. But that's not a good description of the path, right? It just doesn't tell us where we need to go to reach that destination intersection. There are ways to fix this, and we'll fix this later because we'll show you how to return the actual path. I'm not going to do this for the depth first search, but keep it in mind. We will do it later. Okay. So I showed you this important algorithm because it's something that students often think about, because you've used recursion before in ECE294. And but it's not a great algorithm to use for our case. I'll show you a demo right now from our golden solution and show you why it is not a very good solution. Okay, our graphs are really big. The Toronto map, for example, have more than 200,000 intersections. Tokyo has more than 1 million intersections. First, we will try to find the time complexity of this algorithm and see whether it's a good algorithm or not. Okay. So in ECE244, I think you analyze time complexity of similar recursive functions. Anyone has any idea what is the time complexity of this? It might be difficult, but anyone wants to take a shot at it? Sorry? Yes. Yeah, B09. It's O of n, right. Do you know, can you explain why? Okay, yeah. So what do we know in this algorithm? First, that we mark each node as visited when we visited it, okay? And that simplifies the time complexity analysis a lot. Why? Because all we need right now is to find the time complexity of one find path only, okay, and multiply that by n, where n, let's say, is the number of intersections in the map, okay? So if we look at this function, we have this for loop, okay, that goes over each edge, or each neighboring intersection once, okay? In a typical map, the intersection will be connected to, like, let's say, four other intersections. That's a typical city map. You won't find any city where each intersection is connected to every other intersection. That's not even a feasible city anymore. Okay, so we can say that there is constant time at the beginning of the function, just checking the base case, and in each visit to the children, we are doing also constant work because we are marking this as visited. Okay, so the find path, the find path for one node only is constant time. If we multiply that by n, then our time complexity is O of n. And that's actually pretty fast because this is the best we can do. We are visiting every node only once in the city. Okay. Is that clear? Yes.
Yeah. So can you explain why flight path is constant? I think it's totally different.
Yeah.
But why is flight path constant?
So we will go back. So are you convinced that because we mark each node visited, then we only have to measure the time complexity of one visit, of one transition of this function, or one implementation of this function? So we don't have to do the recursive analysis anymore. Are you convinced about that? Right?
But is it still recursion?
Hmm?
It's still recursion.
It's still recursion, but what are we doing? In the worst case, let's say that you set your source at some intersection in the far east of the city, and the destination is the far west of the city. Okay, because we are doing recursion and marking each intersection as visited once, you will end up visiting, let's say, every node, right? Because you mark them as visited, you will not visit them again, right? So you are visiting every node once. So all we care about is finding the time complexity of one implementation of this function. We don't care about the recursion anymore, right? So if we take this out of the equation now, like the recursive line, you can see that all of this is a constant work because the number of edges connected to each intersection is around 4. It's like something that can be counted on hand. Exactly, it's not a very large case, right? So we call this as constant work. Yeah. Yes. Yes. And then because we are visiting each node at once, then you multiply that constant time by n and you get O of n, right? Yeah. Any other questions on this? Okay. So I'm going to do a quick demo from the golden solution that we have. You will see that it's not a very good golden solution, but I want to show you why, like give you a motivation why depth first search is not a suitable algorithm for our use case in this milestone. Okay, so you guys see this? Yeah. Okay, so in our golden solution, let me just make this in the video. Yeah. In our golden solution, while trying to visit every edge or every node, we try to draw the current edge that we are visiting, okay? So that just for debugging purposes, we want to see how the map is being traversed while doing the algorithm. And this drawing is very fast, so to slow it down a little bit and just for me to be able to see how things are going, we add this delay function and we pass to it 1 millisecond. So that means after visiting every edge, we are just delaying this 1 millisecond just for me to see how the algorithm is progressing, okay? So I'm going to, I think I compiled it, yeah. So this is our golden solution. Aesthetically, it's not the best map, but we use it to debug some of the reference solutions that we have to test your unit, for the unit test that we provide you, okay? So if you see here, we have multiple algorithms, and right now it's set at the depth first search, which is the current algorithm that I want to demo, okay? So let's say the source intersection is set somewhere around here, and I set the destination intersection by clicking here, okay? So you will see how the map is progressing. And, oops, no, that's actually not the first search. Okay. Okay. So now you see that it is trying to find a path randomly. There is no other information about the travel time here. We're just trying to traverse all the nodes. And you can see that it might end up visiting every intersection in the city until it gets to the destination. If there is a path, it will eventually find it, but you can see that it's not a very good solution, right? Like, we are doing a lot of work. So let me make this a bit quicker so that we can see the solution. Okay, so I'm gonna stop it here, compile again. So right now I set it to 0.5 millisecond. You will see how much of a difference that 0.5 millisecond makes. Oops. So let's make sure that it is set. Okay. So let's say click here. Okay. Now you see that with 0.5 milliseconds faster, now the drawing is much faster. Okay. We printed some information about the path, and it tells us that we need 3,000 minutes to get to that destination. Obviously, this is not a good. This is a terrible Uber driver, and you'll end up. Yeah, you see, like if we visit another node now, it's taking 4,900 minutes. Okay. So that's why depth first search is not a good algorithm for us. We don't have any information about the travel time. There are ways to fix this recursively, but it's very complicated. And that's why we want to learn better algorithms that are easier to understand and easier to code. Okay, any questions on this before we go? Okay. Okay, so from this demo, we are convinced that the path quality or the path that we are finding is not that good. And we want to find something better. Okay, so for example, even in this small graph, it might be better to just go straight to the destination. Okay, so if you do that only for milestone 3, you'll probably get low marks, and your TA will be pissed because it's not, your map is not usable. It's a very bad path. Okay, so how do we fix? So that now it's a segue to our second algorithm, which is called a breadth first search. Okay. So let's look again at how that first search works. It basically wanders around the city, trying to visit any node that we haven't visited before, in the hope of finding the destination intersection. If there is a path, it will eventually find it, okay? But if I give you like a paper map like this, and I tell you that I want to go from this intersection to this intersection, what is the intuitive thing that you can do? You probably don't want to look randomly, right? So you have to guide the algorithm somehow to your destination. So, and when we get to more complicated algorithms in this course, it's actually pretty good to think about how you will do this, not with a computer, on your own, because that will give you some intuition on how to code the algorithm, right? So anyone wants to guess like how to tackle this? Yeah.
Would it possibly be to look at all the connecting intersections from your given intersection and see whichever either is the closest or the fastest, like some weight to determine which is the fastest?
Okay. Yeah. You're on the right track. Yeah.
Maybe what you could do is you can take like the distance between the two points, add some extra like factors, times 1.5 for example, and then as you're tracking, your different possible paths, if the time taking gets longer than that 1.5 times whatever the distance.
Yeah, that's also a good idea. So you're basically trying to guide the algorithm towards the destination intersection by measuring what's the distance right now from where I am to the destination. Yeah, that's a good idea. And actually, when we get to the more complicated algorithms that you will need to implement for milestone 3, we will use some kind of that intuition. And yours is basically true as well. Like, let's not do recursive thing and try to visit where we are right now. Let's visit all of the intersections around me right now first, and then see if the destination intersection is around me or not, okay? So we call this as a wavefront expansion. So let's say that I draw a small radius around my current intersection first, right? And I try to visit every intersection in that small radius. If the destination intersection is one of these, that means we found a path, right? Because there'll definitely be a path going from that source. If not, then I visit the nodes that are reachable from those nodes in that radius. So I basically make the radius bigger, okay? And I visit all the nodes that are reachable from here. I keep doing this little by increasing this radius until we find the path. Okay, now in this case we found a path. It's way better than the big loop that the depth first search did. Okay, and this is called breadth first search. Instead of going depth-wise, we're basically going breadth. We're visiting all of the nodes that are reachable from my current node first, and then expanding from there. This is one of the most important algorithms in graph search, and I actually almost always ask it to any candidate who is interviewing at Cerebrius to implement a breadth first search in the interview. Because in AI compilers, we use a lot of graph algorithms, and one of the most basic ones that you need to know is the breadth first search. Okay, so how does this work? So let's say we have our source here, and we are trying to count the number of hops that are reachable from my current source, okay, from my current node. So the closest points that I can, or the closest nodes that I can reach from the source are 1 hop away, and I try to visit them first, okay? If my destination is one of them, that means I found the path. If not, I continue doing the 2 hops away nodes, okay? I'm visiting all of these nodes. The destination is not here. I'll continue going to the next, and now, okay, my destination is 3 hops away. I found the destination. That means there is a path that I can find. Okay, so we will continue doing this, the same definition of the function, but now it's called the BFS path. We are given the source ID and the destination ID, and we are trying to return a Boolean, whether a path exists or not. Okay, so this algorithm is not recursive anymore. We will see how to implement it, and it's way better than the depth first search. Okay, so this is the code for it. It's a pseudo code. It's not exactly the code, but we will go over it in a bit in detail, so don't freak out if it's a lot of information. Okay. So remember, we defined this radius on that paper map, okay, and we saw that we are expanding that radius. We call this a wavefront, okay? So this wavefront, all it does is that it stores all of the nodes that are, all of the candidate nodes that I want to visit next, okay? So at this, after visiting the source intersection, the wavefront will be populated of all of the reachable nodes from my current, from the source intersection, and from there we're going to expand. So the first thing that, I'm defining this as a linked list of intersection IDs. There are multiple ways to do this. The best way is actually called queue. Have you covered queues before? Yeah, okay. So we'll talk about them later anyway. And the first thing that we need to do is to push our source intersection into that wavefront. So the first candidate node that we want to visit is obviously the source intersection, right? And then we keep looping until there is no more candidate nodes in the graph, in the wavefront, okay? So we will keep doing this. The first thing that we always do is get the first node in the wavefront, the next candidate node that we want to visit. And usually this is at the front, okay? So we take the front node and then we pop it because we want to visit it and we don't want to add it again to the wavefront. So that's always the first thing that you do in a breadth first search, right? We will also mark it as visited because, again, we want to break the cycles. So we will have to check if this node has been visited or not, because you will see from the examples that I'm going to show is that a node might be added to the wavefront multiple times because it can be reached from multiple different intersections, right? So but we only need to visit it once. So if the node has been visited, just skip it, okay? Otherwise, set the visited flag to true. Now, if my current ID or if the node that I just took from the wavefront is the destination intersection that I want to find, that means we found a path, let's return true. If not, then we do something similar to what we did in the depth first search, and we try to visit all of the nodes reachable from my current ID. And these are usually just the direct neighbors, or the 1 hop away from where I am right now. But in this case, we don't call the function recursively. All we do is that we get the neighboring ID, right? And we push it to the wavefront, right? In milestone 1, we showed you in the library how to get the to and from intersections from each edge. You will use that to get the ID and push it to the wavefront. That means that this node is one of the candidate nodes that I want to visit later. Might not be the next node that I'm going to visit because the wavefront list might be already populated with some other candidates, but eventually we will visit that node. Okay, and we keep doing this until the wavefront is empty. If the wavefront is empty, that means we couldn't find any intersection, any path that reaches the destination, so we will have to return false. Okay, so let's apply this to this small example here. First of all, any questions on this? There might be a new code. Yes, go ahead.
Is there any reason why you did a list of a vector?
Because it allows us to
Properties? Like, does the vector have those like two properties?
yes. So the linked list has the properties of a queue, because the first node that you push to the queue, you will have to it will be the first node that you want to visit, right? In a vector, if you remove the first node in the vector, it's an O of n operation because you will have to shift all of the other nodes left. So it's way more efficient to visit the queue, to do a queue or a linked list, right? Yeah. Okay, so there are no other questions. Let's look at this example. So this is my source. At the beginning, my wavefront is empty. The first thing that we did here is to push our source to the wavefront, right? So we pushed this node 0, okay? And now we are going to go through this loop. So we are visiting the source. We depopulated the wavefront and removed the node 0, okay? And what we did is we pushed nodes 1 and 2. These are the ones that are reachable from current node 0, so we push them directly to the wavefront. Now, we didn't find the destination, so we'll go into another loop, another iteration of that loop. Okay? So the first node in the wavefront was 1. We will take it and remove it and try to visit it. This node hasn't been visited before, so we will mark it as visited. And now we will store its children or whatever neighboring edges, neighboring nodes in the wavefront. So in this case, we add 3. But in the next iteration, we don't visit 3 directly. We first visit 2 because it's currently the first candidate node to visit, right? So we visit 2, and it has two neighbors, 3 and 4, so we will push them. Now notice here that we pushed 3 twice, right? Because 3 is reachable from 2 nodes, from 1 and 2. So because we are using this visited flag, that means we are guaranteeing that we will only visit it once, even if it occurs multiple times in the wavefront. Okay, so the next iteration, we visit 3. It's not our destination, so we push its children to the wavefront. So we pushed 5 here, and we visit the next candidate. In this case, it's 4. There are no more edges reachable from 4, so we just return, don't do anything here. Okay, we visit 3 again. 3 in this case is visited already, so we don't do anything. We will not push 5 anymore because we've already visited. And finally, the last node, that's actually not true because we continued here, so we don't push. So this is not true, actually. We shouldn't push 5 again. And finally, we reached 5. It's our destination. We haven't visited before, okay, that now we can return to because we know that there is a path going from the source to the destination. Okay, any questions on this? You probably have to go through this algorithm by hand to get a sense of it because it's one of the newest algorithms that you'll probably learn. Okay, so what do we know so far? Again, we are only returning a Boolean, whether a path exists or not. And that's not what we want in milestone 3. We want you to return the actual vector of street segments that constitute the path going from the source to the destination. Okay, so, but from this algorithm, I don't know much. I only know whether the destination is here, right? So we use a technique called backtracing in order to find the actual path. So right now, we don't have much information. So we need to add some kind of a new data structure that gives us more information in order to be able to backtrace from the destination back to the source and find the actual path that we found, right? So the way we do this is that at each node intersection, we store the street segment that got you there. So whenever you visit a new node, we want to have information of where you got to that node from. So what is the intersection that allowed you to get to that node? When you reach the destination, because we stored all of these edges, we follow these stored edges, backtracing it, starting from the destination back to the source, and store all of the edges in that path. That means we found the path that got us there. And this creates the whole path that we will return. Okay, so how do I print out the path? In order to do this, we will have to add additional data structure to the algorithm that we just saw. We actually need two additional data structures. We need more to store this information. The first one, I call it here wave element. It's something that I will push to the wavefront. Instead of just pushing an intersection ID, I'm gonna push more information into this wavefront. So in it, we'll obviously store the intersection ID because we wanna store the next candidate nodes that we wanna visit. In addition to that, we will also store the street segment index, which constitutes the edge that got us to this current wave element that we're going to visit, or the current candidate that we're going to visit. So it is the edge used to reach the node, whatever node in here. And for conveniency, I'm basically creating a constructor here that will initialize this wave element to a certain intersection and an edge, right? Okay. I'm also going to define this global parameter that doesn't change, just for me to know that, let's say at the source, because I'm starting at the source, there is no edge that allows me to get to that source, right? So I'm just gonna define this, what we call it a sentinel case, so my algorithm can stop at, and I'm calling it no edge. So once I reach a node with no edge at it, that means I'm at the source, I can return no. And for convenience, I'm just gonna set the value to -1. The street segment index is usually an integer, so a -1 is not a valid index anyway for any street segment index in the map, so it's a valid one to use to just stop my algorithm. Okay. The second node, the second structure that I want to expand is this node data structure. So far, what we've used from this node data structure is what are the neighboring nodes reachable from this node, and whether this node has been visited or not, right? So on top of that, I'm going to store a new one, which is called reaching edge. That means what is the edge that I use to reach to this current node? And I'm gonna show you why we need this in a little bit. Okay, so remember we used this in the algorithm. We used it to go over all of the neighbors. There are ways in Myson 1 that allows you to do that, and whether this node has been visited or not, so that we break the cycles. Now we're going to store the ID of the edge that used to reach to that node again. Okay, so we're going to expand our algorithms in this way. Sorry. So instead of pushing making a list of intersection IDs only, we are making now a list of wave elements. Remember, a wave element is some kind of a data structure that represents the candidate nodes that I'm going to visit next. Okay, and when we push back a new wave element with source ID and no edge, meaning that there is no edge used to reach to the source ID because it's the first node in my search algorithm. Okay, and then we follow the same algorithm. It's the same kind of loop, but notice here that whenever we use an intersection index, we're just using a wave element. Okay, so we are taking the first wave element from the list. We are setting it to true here again to mark it as visited. And notice here that on top of setting the flag to true, we're also setting the reaching edge to the current node ID to be the current edge ID. Okay, so now we are visiting a new node, right? This new node has two elements. It has the intersection index, which is the node ID, and it has an edge ID, which is the edge used to reach to that node from the previous iterations. Okay, so we use this to update the global data structure of the nodes, right? we want to store for each node what is the reaching edge we use to get to this, to this intersection. Okay? We continue to do the same thing by visiting all of the children, and instead of pushing just the intersection ID here, we are pushing the intersection ID along with the outgoing edge ID. So remember here, we are visiting every outgoing edge from the current intersection. We use those IDs to store information about what is our, what is the edge, what are the edges that we use to get to those IDs. Okay, I know it's a bit, it's a lot of code, and you probably again need to go over it in detail, but I hope you got the idea. If you have any questions, let me know. Any questions on this? Yes, Dante. This?
So, yeah.
Yeah.
So, that edge ID is talking about at this current node, how we got to it?
Yes. So it's storing information so that once we find this algorithm returns true and tells us that there is a path exists, we were going to implement in a little bit of another function that backtraces us from the destination back to the source to find the actual path that we found. Okay? And we rely on these new data that we store. Okay, so let's visit again this graph, but with the additional information that we visited. Okay, so we are starting at the source. We are populating the wavefront with the node ID 0 and the edge ID no edge, because at the source there is no edge we use to reach to that node, right? Okay, we visit the source by removing it from the wavefront. And now we will push to the wavefront node 1 and 2. But on top of node 1 and 2, we are also storing the edge IDs. Here I'm calling them A and B, right? Okay, so we visit the next node, which is 1 again. We know from node 1 that we reach to node 1 from A. We store that in the node's reaching edge, okay? And then we push 3E to the wavefront. I'm not going to go over this in detail, but basically we keep doing this one by one until we reach the destination. So we know that we reach to the destination from edge F, right? So starting from this edge F right now, in the next slide, I'm going to show you how to go back to the source. Because we have this information. We know each edge we use to reach each intersection in the map. Okay, so the first thing we did in our main is calling the breadth first search algorithm and seeing if there is a path found or not, okay? The next thing, inside the breadth first search, we store the information that we need to backtrace. So the next thing we do is that if we found a path, that means there is a path that exists. I want to return it. So I'm going to write another function that is called breadth first search traceback. Okay, just tracing back the path. And we start at the destination ID because we are going to trace from the destination back to the source. Okay. So I'm going to use a list here, a linked list of edges. Okay. At the end, this is another function that you can write. It's called make vector from list. It just basically converts the linked list back to a vector because in Milestone 3, we ask you to return a vector, okay? But for convenience, I'm just going to use a linked list to be able to push and pull. Okay, so we define a list of edges called path, and the first thing that we do is we get the current node ID, which is currently the destination ID. I'm starting at the destination, right? So we are starting here at node at destination, and what do we know? We know that the previous edge, or how we got to the destination is through edge F, right? So I store something called previous edge. Again, this is a pseudocode. And we use the information that we stored in the previous algorithm. So remember in the previous algorithm that we have this global node data structure. And each one is storing the edge that we use to reach to that node. So we define the previous edge to be the reaching node. In this case, it is going to be F, right? And then inside a while loop, we start tracing back. So while the previous edge is not equal to no edge again is a stopping criteria that we define to -1, and that's only set on the source intersection. Okay, so while it's not equal to the no edge, we do this. First of all, we push front to the path the previous edge. Okay, so it's going to be one of our path. So in this case, we pushed F, and then from milestone 1, you used some of the library functions in order to get the current node ID that we used for that edge. So in each street segment info stores you the to and from intersection, right? So in this case, our to intersection is the destination. We use it on F to get the from intersection, and that's our current node ID right now. Okay, so in this case, we got this node, and we update the previous edge at this node, right? So in this case, we use the global data structure again to get the edge that we used to reach to that node, which is in this case E. We keep doing that, and notice here that we are populating the path one by one. So right now we have E and F. We visit this node next, okay? We used edge A to reach to that node. We push A to the path. Now we use this node next. This node is source, but the previous edge is what? It's no edge. That means our path, this is our full path. We reach the source, right? Okay, so our path constitutes of A, E, and F. And the reason I use a linked list here is that because we are tracing back, I can push to the front so that my path will be in order at the end. If you use a vector, you can do that by using pushback and then reverse it. There are methods to reverse the vector. Any questions on this? Okay. So, breadth first search is a very important algorithm, but it still doesn't do the job for our map. Why? Because in our map, we told you, in our milestone, we told you that we want to return the path with the minimum travel time from the source to the destination. But that might not translate to the minimum number of nodes visited. Let's say if the requirement was to find the minimum number of edges or the minimum number of nodes to visit, then breadth first search would give you the optimal solution. Why? Because we will consider it as what we call it an unweighted graph, and we are guaranteed to visit the minimum number of hops to get from the source to the destination. But because we want the travel time, let's look at this example first. Okay, so let's say our source here and our destination, and each edge has a label on it or a weight that represent the travel time to get from one intersection to the other. Okay, so let's say we pushed 0, and we pushed 1 first to the list and then 2, right? Okay, so we visit node 1 next, and we said that the reaching edge from node 1 is through A. Okay, this is where we got to node 1. Okay, so we visit the wavefront again. Now we're visiting node 2, and we store node B, edge B. Okay, but when we visit node 2, we are going to push node 1 again to the wavefront. But later on, because it has been marked visited, we won't visit it again, right? Okay, so now we visit 3, next, and we push 4. Next, we are visiting 1. But again, we're not doing anything. We're not updating the reaching edge from 1 because we visited it before, right? So we check that the visited is true. We're not gonna do anything. So we remove it from the wavefront and just push, just visit the next one, which is in this case 4. Okay. And we found our path. Our breadth first search told us that a path exists already. Okay, so we found the path, but it's not the shortest. Why? Because if you sum up all of the travel times along this path, we are adding 15, 6, and 3. But if you notice that if we go through B and C instead of A, we are doing 5 and 5. Okay, so 10 is less than 15 basically. So because our breadth first search algorithm currently doesn't have any information about the travel time, it does not guarantee the optimal solution to our problem. Okay? So node 1 only visited once because we are relying on this visited flag. Okay? So, sorry, this is a suboptimal path. There are ways to fix this, and we're going to introduce this in the next lecture. Right now, I'm just going to show you a demo of breadth first search. But the way to fix this is to take into account the travel time. And if we visit a node that has already been visited before, we check the current travel time to get here. If it is less than the current the travel time that we use to reach to that node first, then we update the global data structure. If it's not, we just skip it. This algorithm is called Dijkstra, and we're going to introduce it in the next milestone, in the next lecture. But first, let me give you any questions before we go into the demo. Nope, okay. Okay. So right now I'm going to change the algorithm to breadth first. And okay, so you can see how the wavefront is expanding, right? One by one to get to, like my source was around here and my destination is here. So it visited a lot of nodes until we got, and this represents the wavefront, until we got to the destination. Now in this case, I think we were lucky and found the shortest path because it used the highway. But again, it does not guarantee it, and we're going to see why in the next lecture. So let's say do this again, and basically it's expanding. Okay. So another problem with the breadth first search is it's also expanding. That means sometimes we are visiting nodes that we know for a fact that we don't need, right? And we're going to rely on the fact, your friend here suggested that we're going to take the distance into account in order to determine which node to visit next, in order to constrain the search space for our path, so we don't have to visit the nodes that we don't need to visit. And this will minimize the overall CPU time of the algorithm. Again, we're going to cover this in the next lecture. Any questions? I see a lot of confused spaces, but that's fine. It's a new algorithm. So, okay, if not, then yeah, this is it, and we'll see you on Thursday.